So let's look into current regulator. So far we have been talking about only voltage regulator. You are regulating the output voltage, but there are some certain applications where you need to regulate the current. So applications, the most common application is your battery charger. So how does it work, your battery charger? Now let's take the same regulator. You have Vref, Vin, this is your charging current. Now let's say this is your battery. So now since your reference is mostly a voltage reference, so which means I need to convert this current into a constant voltage and compare that. So all I need to do, put a sense resistor, and most of the time this is external off chip because we need a very accurate sense resistor. Okay, so now what will be the charging current? I charge equal to Vref by R sense, and Vref is constant. So depending upon what Vref is, you choose the R sense and you define the current. So if you want a 1 amp and Vref is 1 volt, then you need to put 1 ohm resistor here and it will give you 1 amp constant current. Okay. Most of the time this is order of tens of milliohm. We don't use such a high value because you will be losing I square R losses there and you don't want to lose efficiency. So due to efficiency reason, most of the time we choose order of tens of milliohm or at max 100 milliamp or so. So that your Vref you can choose 100 millivolt and you for 1 amp current choose R sense of 100 milliohm. Okay. So that this is the one application. What could be the other application? Biasing? No, but for that you don't need regulator. Huh? LED driver. Okay, so you have this LED and this requires a constant current. So again do the same thing, R sense. Vref correct. So LEDs require constant current, and if you look at the data sheet, they have a maximum specified current. If you supply more than that current, these LEDs may heat up and break. So that's a one thing, like you have to limit the maximum current, Other thing is the brightness control actually. These LEDs, the brightness of these LEDs is proportional to your current. So, if you reduce the current, you can dim it, and if you want to increase the intensity, you increase the current. And most of these dimmable LEDs use current regulators, and you simply control the current. Okay. These days you would have seen this, there are bulbs, remote controlled bulbs, where you can control the brightness. They do nothing but those signals control the current in the LEDs. So, two ways you can either if you have a way to control the R sense, you can change the R sense, or but most of the time we use VREF, because R sense usually if it is off chip difficult to control, but if you have a on chip you can build a RDAC, but usually these values of order of ohms, so you cannot get very good resolution, which means you have to have a smallest resistor in order of milliohms, which is not easy to build. So, you just control the VREF and get the variable current, which will control the intensity of your LED. So, this is used to provide constant voltage reference across process voltage and temperature. So, this is your regulator. And this VREF come from band gap reference. And what do you want this VREF to be? Constant across process voltage and temperature. The reason is if VREF changes, your V out will. So, V out is directly depending upon your VREF, and we have some accuracy spec, we already talked about that. So, if VREF is not accurate, then your output will never be accurate. So, that is why your VREF has to be very accurate. So, why do not I do this? If I have some VDD R1, R2 and just use this VREF. What is the problem with this? Why temperature dependent? But what is the VREF expression? Can you tell me? R2 upon R1 plus R2 into VDD. So, let us say VDD is 2 volt and I want VREF equal to 1 volt. What should be the? So, which means R1 equal to R2 It's not depending on resistor, huh? So what temperature will matter here?
Like they have slightly different temperature coefficients over
Who has slightly different?
R1 and R2.
How come? Why different? I don't understand. If they have they are same type of resistor, why they will have a different temperature coefficient? So temperature is not a problem here. The problem is the VDD. If your VDD is not constant, your Vref will not be constant. So that is your voltage dependence, not the temperature dependence. Okay, so you can always do this without any problem. Where is that? Okay. Okay, what could be, is there any other way I can generate Vref, constant Vref? What is the forward voltage of diode? Hmm? So this is any I bias. Can I use this as a reference? 0.7 volt. This will be constant. So maybe with the VDD it may not change. Okay, but what about temperature and process? Okay, so this is not constant across temperature. Temperature, okay, but we will use the same diode concept to build the band gap reference. Okay, so we need reference to be constant across so this cannot work. So what is the, so if this is your what is the collector current of your bipolar? IS into VB over VT. What is VT? No, what is that actually? Thermal voltage, okay. So if I want to write the expression for VB, what will be that? VT and IC by IS. Okay. VT is KT by Q. K is constant, Q is constant. So this is VT is, and T is the temperature. So what is del VT? What is K? What is the value? Unit? Okay, and Q?
Q 1.6 into 10 power minus
19, huh?
8.
So substitute here. What is this value?
0.857 10 power minus 4.
86 millivolt per, correct?
Right.
So what will be the Vt at room temperature? Vt how will you find Vt at room temperature? What is the temperature at K at how many kelvins you have at room temperature? 300. So just multiply 86 by 300. Huh? How much is that?
25.8.
Yeah, roughly 26 millivolt. That's what you have. Huh? Vt value is given as 26 millivolt at room temperature. Correct? That's where your 26 millivolt comes from. So the concept of band gap is generated from there only, and that is called, so Vt is proportional to temperature. Okay. So if I want to generate a band gap, if this is my temperature and this is my Vref. So if I have one voltage which is proportional to temperature, if I can get another voltage which is inversely proportional and add up the two, then you can get a flat voltage. Okay. So let us say I have this curve and this curve. So if I call it V of Ctat and if this is V of Ptat, complementary to absolute temperature and proportional to absolute temperature. So we call it Ctat Ptat, and this is Vctat plus which becomes your Vref or Vbg, which means what I am looking for, delta of Vref over delta of T should be 0. So what is the condition to make it 0? The slope should be same. Huh? If slope is not same, then they will not cancel out. Which means delta of Vp tat over plus delta of should also be 0. This implies should be exactly opposite to and you already know that this Vt has 86 microvolt per Kelvin. So now what we need to do, So, VT you can generate, you already know how to generate the VT. VT is coming from your VB current. The current expression had the VT. If you write in terms of your VBE, okay, it has a VT term there, but it has also two more component, IC over IS. So, overall behavior actually becomes a negative for VB, even though your VT has a positive coefficient, but your IC has a negative. So, but the resultant effect is negative. So, VB has a negative temperature coefficient. So, your VB was VT ln IC over IS. Okay, and this is usually minus 1.5 millivolt to minus 2 millivolt per Kelvin. Okay, that is the slope. It comes from the process itself. Okay, so different process you might see some variation, but usually it remains within that. So when you use do your simulations, you can find that number by doing the simulation. So all you need to do, just plot the VB across temperature and you will get that number. So that may vary across the process, but most of the time it will remain within these numbers. So VB already know, and since it has a non-linear term, ln IC over IS is not linear term. So there has to be some non-linearity here. So this doesn't exactly look like this, but it has some curve like a parabola. So this is your ideal and this is your real curve. And most of you who have worked on band gap, they would have seen the output is actually has a curvature. It is not a flat, and that curvature comes from here only, because VT is linear. VT does not have any non-linear component, but VB has. So that non-linearity comes from that VB. So now you have a voltage which is proportional to. So which voltage is proportional to temperature? Your VT is proportional to temperature. Okay, and because that is kT by Q, so that is perfectly linear, and you have a inversely proportional to temperature which is VB. If can I simply add up the two and get the band gap?
To make the slope equal.
Yeah, so slopes are not same. This is minus 1.5 milli and that gap was 86 micro or so. Okay. So which means I need to change the slope of the other guy, the delta VB, or sorry, the VT term. So how can I do that?
Slope of VT cannot be changed.
But you can add some coefficient. You can design in such a way that